Hi guys, this is the first of probably many screencasts where I go through some of the PowerPoints. So the next chapter that we're going to talk about deals with earthquakes. So we'll kind of go through a little bit of this, and then I'm going to have you guys watch a video that's pretty good. So earthquakes are the vibration of Earth produced by the rapid release of energy. They're mostly associated with movement along faults. We explain this by, plate tectonic theory. I know you guys know this stuff. This is pretty basic. The mechanism for earthquakes was first explained by H. Reed. That's not something that you necessarily need to write down. But the next part's kind of important. So the rocks basically spring back, and this is what we call elastic rebound. So vibrations occur as the rock elastically returns to its original shape. And the next slide will kind of show you what we mean by that. So if you look at the top picture up here, this shows just a little bit of strain, but for the most part, there's not tons of strain. And then the strain builds into the second picture. And the stick over here is just to show you kind of like give you an analogy for what happens. So first, the strain kind of builds up, and you can see the right side of the plate is going down, and the left side of the plate is going up. So it's like you're adding that tension, and then it moves a little bit further, and now there's a bend in the stick, and then eventually the stick will break, and the break of the stick is analogous to the earthquake. And when you get an earthquake, that's when the plates actually move. And they're showing this as being blurry because they're showing that trying to show that it's vibrating, just like the vibration of the stick over here. And then after the earthquake is over, then the plates have gotten to some sort of new normal where they are offset. And if you go out to California along the San Andreas Fault, we see many examples of different places where this has happened, where you have streets that are offset, or curbs that are offset, or sidewalks or fences, things that are supposed to be straight that lie along the fault where there's been some slippage along that fault. So here is the San Andreas Fault. I know you guys did an assignment with it earlier. So you basically have the Pacific Plate going this way and the North American Plate coming this way. So this happens all along here. Another type of fault is called a megathrust fault. This is the type that causes really big earthquakes. As a general rule, things like the tsunami that occurred in Japan, where you have a subducting plate that's going down, and then you get stress that builds up in kind of a curling down direction, and then when that slips, it pops up. So that's called a megathrust fault. These individual faults over here in the mountain range are just called thrust faults. So earthquake waves, the study of them is called seismology. So 3 seismo words here. So seismology is the study of earthquake waves. The instrument that we use to record our waves is called a seismograph, and the record that it keeps is called a seismogram. So that's the actual piece of paper that has the little squiggly lines on it. And here's an example of one. We drill these down and put them into the bedrock so that they can really accurately get a sense of how much movement there is. And it's basically got an arm, a vertical arm here, and then a horizontal arm here. And this is connected by a wire. And then, so any vibrations allows the horizontal arm to swing back and forth. And the drum rotates underneath it. And then we record how large the vibrations are. So we have different types of waves. Some of these you guys have probably heard of before. We have primary waves, or P waves, which are push-pull. And here these travel by a series of what we call compressions and rarefactions. Compressions are where you have the places squeezed together, and rarefactions are where they're spread apart. So the example that they're giving here is a slinky. If we were in class, I actually have slinkies, and I would do basically this very same thing with you. So this is how P waves travel. So P waves are a type of what we call a longitudinal wave that travels through this push-pull compression rarefaction action. Next kind of wave is called an S wave. So the S wave is up and down. You can see this travels through a series of crests and troughs. The crest is the top of the wave, and the trough is the bottom of the wave. So secondary waves or S waves travel this way. So particle motion there is up and down. And then the final is called a surface wave. And here the motion of the particles is actually a circle. Most complex motion travels the slowest. Least earthquakes have these. Almost all of them have P waves and S waves. So how do we locate an earthquake? So one way to do it is with what we call the focus, which is the actual place within the earth where the earthquake waves originate. So that's where the slip actually occurred. And then the epicenter is actually the point on the map above the focus. So we can locate this using the difference in arrival times between the P and S wave recordings, which are related to distance. So the longer it takes in between the P wave and the S wave, P stands for primary, S stands for secondary. So the P waves are faster than the S waves. So the primary waves will race out in front. Secondary waves will go a little bit slower behind it. So the bigger the gap between the P waves and the S waves, the farther away it happened. So this is just a picture showing you here's where the focus is, or another name for it is the hypocenter. Above that is the epicenter, and the crack here is just the fault. Okay, so you have the fault, focus, and epicenter. So locating an earthquake. So in order to do that, you need 3 recording stations to locate an epicenter, and you basically from each one, you'll figure out how far the earthquake was from that recording station, and then you can draw a circle. So from any one recording station, all you would be able to tell is how far away was it from that recording station. Was it 100 miles? Was it 200 miles? Was it 500 miles? Was it 1,000 miles? And you could basically just draw a ring. Well, if you have two recording stations, then you would have 2 circles, and then those circles would overlap in usually 2 places. Where those circles overlapped in 2 places, those 2 points would be your potential places where the epicenter was. So you need a 3rd circle to actually be able to tell you that yes, it occurred at one of those points. So wherever those 3 circles from the 3 different recording stations that's where the epicenter occurred. This is just showing you how we can see this. So this is the P wave, S wave, and surface wave in order. P stands for primary, once again, S stands for secondary. So the greater the difference between when the P wave gets there and when the S wave gets there, the farther it was. So you can see if you look at where the epicenter was, and then you look where the first seismograph was versus the second seismograph, the farther away you get, the larger the distance is between the P waves and the S waves.